All right, so Jad is going to talk about staircase personalization and constraint dynamics in lattice gauge theory. So Jad, let me not eat up more of your time.
All right, so Achilleas, thank you and everybody for having me here in this seminar. Today I will be discussing a part of my research that I've been doing over the year and a half as a postdoc in the group of Philip Hauke at the University of Trento. Well, originally we started at the University of Heidelberg and then we transferred to the University of Trento at the beginning of the year 2020. And today's talk will mostly cover our work on lattice gauge theory implementations in ultra-cold atom setups and how to enforce gauge invariance and the intrinsic behavior of gauge violations due to unavoidable gauge breaking errors in these implementations. So as you know, gauge theories are fundamental theories of nature that describe interactions between elementary particles as mediated by the gauge field, or gauge bosons, if you wish. And the problem with these gauge theories is that they are notoriously difficult to simulate classically. As such, we turn to the wise words of Richard Feynman from 1982, and we try to implement these theories now on quantum simulators. And especially in today's experimental setups in ultra-cold atoms and digital computers as well, you see that we have a great level of precision and control. And this basically forms a great test bed for these theories where we can actually implement them in a much cheaper way than, let's say, building an accelerator. I'm not saying we're replacing accelerators or anything, but now we have the capability of gauging these gauge theories and looking at their behavior on low energy setups. And in this spirit, there has been a flurry of research, experimental research, implementing these gauge theories. And here I list some of these works. So here you have ion trap experiments from the blood group. This was in Nature from 2016. Also, there's this Nature by Kokayel et al. A recent ultra-cold atoms implementation was in the group of Fred Jędrzejewski in Heidelberg, where they implemented the building block of a U1 gauge theory. So the local gauge symmetry is a U1 of the U1 type. Superconducting qubit implementations have been by Kelko et al. Here, also with photons, and recently also in optical lattices in the group of Monica Eidels-Puga in Munich, and also by a Heidelberg Hefei China collaboration, and this paper by Yang et al., where I was involved. So this paper is the first extended lattice gauge theory that was implemented on an extended Bose-Hubbard model. We will come to this later. Now, these implementations are all great, but the problem now, gauge invariance is actually a postulate of nature. So in nature, gauge invariance is preserved in a gauge theory. In these implementations, you actually have to teach your quantum simulator to enforce this gauge invariance. Before we dive into lattice gauge implementations on quantum simulators, we want to look at how we can certify results that a quantum simulator spits out. So we have a quantum many-body theory, we implement it on a quantum simulator. How can we trust these results? So a nice paper by Hauke et al. From 2012 raised 4 criteria for the trustworthiness of a quantum simulator. And these are basically reliability, controllability, efficiency, and relevance. In this paper, in this talk, we will focus mostly on reliability of quantum simulators, and in particular, lattice gauge theory implementations on quantum simulators. One of the first papers that targeted reliability of quantum simulators was by Heil et al. It's in Science Advances, and they looked at Trotter errors on local observables. So as you know, on a digital quantum computer, you have this Trotterized dynamics, and basically what this paper found is that if your Trotter time step is below a certain upper bound, your error, your long time error of a local observable will always be controlled in that it will scale proportional to the square of your Trotter time step. Above this upper bound, your long time error will be chaotic in that any small change in the Trotter time step above this upper bound will lead to an uncontrolled change in this in the error of your local observable. And they likened it in this paper to the phase transition between an MBL phase, a localized MBL phase, and a quantum chaotic phase. They didn't show this rigorously, but basically they made this connection. Yes, go ahead.
Is this threshold independent of system size?
Yes, they show that it's independent of system size. And I will show you later also that it is in our case as well.
Great, thanks.
So you're welcome. So results in this spirit when it comes to gauge theory implementations on quantum simulators, the reliability of gauge invariance is of high importance here. To have a gauge theory, you need gauge invariance. And now we will investigate what happens when gauge invariance is slightly broken. How can we protect it? And we see, as we will dive deeper into details later, that gauge invariance is naturally retained over a well-defined timescale, even in the presence of unavoidable gauge breaking errors in your experiment. It can be protected to infinite times. We will also show exactly what we mean by this later. And we have also recently shown in a paper that came out last week that protection works in the thermodynamic limit at a volume independent strength. So this is Stitadi's question from a second. I think that was Stitadi. So let us actually now put on a formal footing what the breakdown of gauge invariance is. We consider the Schwinger quantum link model in one dimension. Here, what you see, the following terms, let me turn on my laser pointer. Yeah. So what you see here are so-called assisted tunneling terms. What this guy does is it simulates the time evolution of the Schwinger mechanism, which is basically the instability of bare vacuum in the form of fluctuations that manifest themselves in the spontaneous creation of electron-positron pairs. So what you see here is these fermionic operators, psi. So psi dagger psi basically tells you about the spontaneous creation of electron-positron fields. To maintain Gauss's law, your gauge field here in the middle must react concomitantly. So at the same time, at the same point in time and space, in order for Gauss's law to be always preserved. M denotes the mass of your matter, and here E squared is the electric field. So in an experimental setup, for example, what you do is you say, okay, I'm gonna model my matter fields as lithium atoms, and I will use sodium atoms for my gauge field. And what I would like to do is to say, okay, if I excite a lithium atom, that means I have created an electron-positron pair, and I want the electric field in the middle to instantaneously flip in order to satisfy Gauss's law, which we write here, but I'm sure all of you are familiar with it. So I excite a sodium atom, and at the same time, I excite a lithium atom to simulate this electron-positron creation, pair creation, and I de-excite a sodium atom in order to simulate the concomitant flipping of the electric field. But you can easily imagine that in an experiment, I would excite a lithium atom, so I simulate this creation of the positron-electron pair, but at the same time, nothing happens in the sodium atoms, which means I have violated Gauss's law. The question is, how severe are such processes? Quite a few works have been done in equilibrium, as we show you here, including a work by ours from last October. And we show that these processes, even though severe, if you have some protection term, which we will dive into later, you can still get a form of a renormalized gauge theory. In this work, we will focus more on what happens dynamically. And there we also see we have emergent renormalized gauge theories. And we will put this on a formal footing in the following slides. So this setup here that I discussed is from the Fred Jędrzejewski group in Heidelberg. And this is a U1 lattice gauge theory building block that they constructed using lithium and sodium species. We can now look at this faulty lattice gauge theory implementations and split it into two parts. We have H0, which is the theory that if we were God, basically, we would be able to implement in an experiment. And lambda H1, these are the gauge breaking terms, because I don't have infinite fine-tuning capabilities in an experiment. I will have these gauge breaking terms H1 at a strength lambda. Schematically, what H naught does is it leaves your dynamics in the gauge invariant target space, basically the subspace of Gauss's law. What H1 does is it drives your dynamics outside of this target subspace. And the question is, how can I ameliorate this? How can I resolve this problem? Again, if we look schematically, just to be precise, you see that this is a vacuum state. So if we consider quantum electrodynamics, this is a vacuum state where I have a field just pointing in one direction, and H naught, processes by H naught, like I told you, this assisted tunneling term, would bring me to the following state. So I have a creation of an electron-positron pair, and the electric field in between them flips concomitantly so that Gauss's law is still preserved. Processes in H1 would be an unassisted flipping of your electric field. So the electric field flips without any movement of your matter fields. This violates Gauss's law. Now, if we look at these errors, lambda at their strength, we see that we have a time scale. So here I'm showing you several values of lambda, and no matter what value of lambda you see, you have an intrinsic time scale over which this violation grows in a controlled way. In fact, you can convince yourself in time-dependent perturbation theory that the violation, and basically here the violation is nothing but the square of the local generator of Gauss's law, because that should be zero if I'm satisfying Gauss's law. We see that over an intrinsic time scale, this violation grows as lambda squared t squared. And then after some time, it goes to some value, which basically is roughly random. The generic expectation from TDPT, time-dependent perturbation theory, is that the error would grow as lambda t, and indeed it does for gauge non-invariant observables, but you can convince yourself analytically that gauge invariant observables will always grow as even powers of lambda t, with the gauge violation growing as lambda squared t squared. So this is already good news without any kind of protection, that we have an intrinsic timescale over which the gauge invariance is preserved, in the sense that you can perturbatively connect to your ideal gauge theory because your error grows in a controlled way that you know. Can we do better? And the good news is, yes, we can do a lot better. So again, we go back to our schematic where I have H naught driving my dynamics in the Gauss's law sector and H1 driving me out of it. How do I suppress this? I just introduce an energy penalty term, VHG. So HG is simply the operator that I use to measure the gauge violation. So the square of the local generator of Gauss's law. What happens is now any processes that want to bring me to a sector where Gx is not zero are being penalized. So it's extremely simple. And schematically, this looks as follows. Now processes of H1 will be very expensive energetically for me. And they are basically less favorable in the dynamics. Naively, one would expect that the time scale would just go from lambda to lambda squared over V. But what we see is that the violation is suppressed as lambda squared over V squared. So here we look at the blue curve, we see that for V equals zero, when I have absolutely no protection, I have this growth lambda squared T squared, and then I plateau. As I increase V, even for small values of V, I see that my violation goes into a plateau, into a steady state plateau. And this plateau goes like lambda squared over V squared. So this robustness for long times is surprising. And the question is, okay, look, you do this in exact diagonalization for tiny systems. Will this persist in the thermodynamic limit? The short answer is yes. And it works fascinatingly well for larger system sizes, as we will see later. So if now you look, go ahead.
Can you show the previous? Yeah, so what is it that goes like lambda over V squared exactly?
So this plateau, the value of this plateau.
The value, the height?
Yes.
Ah, okay.
Yeah, it's suppressed as lambda squared over V squared.
And the time scale to reach it, how does that?
1 over V.
Okay, only V, okay.
Yeah.
All right, thanks.
All right. And so now if you look at...
question.
Yeah, go ahead.
How did you manage to have nothing depend on the intrinsic intrinsic energy scales of H naught?
Well, I mean, because I have V is basically becomes your dominant term. So here I'm looking at lambda over V, and you see that once V becomes sufficiently larger than lambda, and in our simulations, as you will see later, of the scale of 10 lambda or so, you see that VHG becomes the dominant dynamics at a time scale of 1 over V. So you have dynamics from H naught, but you're not going to see it in the gauge violation, because the gauge violation under H naught is exactly 0. So you're not going to see any features of H naught. You will see features of H naught in the dynamics of local observables, as we will show you later. So, and there you can see some intrinsic timescales of H naught. But here in the gauge violation, by definition, you cannot, because H naught is fully gauge invariant. So H naught commutes with GX at every X.
Right, but then the scales in the energy scales in H naught don't even enter the time scale at which the plateau sits in?
No, they don't at all.
Okay.
They don't, and they shouldn't. Because if you set lambda to 0 and V to 0, then no matter what your energy scales in H naught are, your gauge violation is 0. Sure, you introduce errors, and okay, to be specific, maybe they have a factor with lambda squared over V squared. We're just showing you like proportionally how this plateau value scales in terms of lambda and V. It goes as lambda squared over V squared. Yes, it is possible that if you change the microscopic parameters within H naught, you will have some trivial factor to the scale, but it's nothing universal.
But right now, I should understand that this is in the regime where V is much larger than lambda, and both of them are
roughly an order of magnitude larger. Yeah,
and both of them are much larger than J.
No, lambda is quite smaller than J, but it doesn't have to be actually. So here for this specific example that I'm using, it's 0.05 J. But actually, this will work even if lambda is roughly proportional to J.
Okay.
Yeah. All right. And now we're looking at the gauge violation. If we take the time average of the gauge violation or the maximum of it and plot this as a function of 1 over J, we will see again that we have here these kind of two regimes. So one regime for sufficiently large V here. So remember here, I'm plotting it as a function of lambda over V. So the larger V is, so beyond a certain lower bound of V, what happens is I see that these quantities, the maximum of your gauge violation or your time average, or even just the long time value of your gauge violation, you see that it goes as lambda squared over V squared. And below this lower bound of V, then your gauge violation, you can no longer actually get it from V. You cannot anticipate it from V. So here it looks quite clean, but when I show you the end results, you will see exactly what I mean. Analytic explanations for the lambda squared over V squared can be derived in degenerate perturbation theory, which we have done in a PRL from 2020. We have an emergent gauge symmetry. Actually, we have two emergent gauge theories that we will discuss later that we can derive analytically. And we also have other papers that have dealt with this in equilibrium by Chab-Flamia. And this is the paper that where we introduce all this analytics, actually, these following two papers. And we will discuss results from them in the following. So the final product here, I will show you this. So here we tried two gauge theories, okay? So this plot is really important for the following slides. So if you have any questions, please let me know. So here I show you for a Z2 gauge theory and for a U1 gauge theory, also this infinite time violation as a function of lambda over V. This is an exact diagonalization for the following different number of matter sites. So here we're using periodic boundary conditions. So the system size is actually 2L because every matter site has an accompanying link. And you see that again, above a certain value of V, you have this controlled violation, lambda squared over V squared. And below this lower bound of V, I am again in this sort of chaotic regime, right? Where a tiny change in the value of V kind of leads me to some drastically different value of the long time gauge violation. Interestingly here is we look at the spectral overlap. So the spectral overlap, this is, you can think of it as the highest eigenenergy in the Gauss's law sector and the lowest eigenenergy outside of it. And you see that they overlap at the following value of V for the different system sizes that you have. So for L equals 2, they overlap at a lower V. And as you increase system size, you see that this V increases and increases. This already scares us a little bit because it means like, okay, what if we go to the thermodynamic limit where there will always, one would expect there will always be some kind of overlap between the sector of Gauss's law and the sectors where I violate gauge invariance. Will I have to go to V equals infinity? The short answer is no, as we will show in the next slides. So conclusion, which we will back up with results after this slide, is that a faulty gauge theory, so a gauge theory implementation where I have these unavoidable gauge breaking terms, will still be a gauge theory at large enough V. And we will discuss exactly what that means, what large enough here means. So we see two emergent gauge theories using the protection term GJ squared. And adjusted, what we call an adjusted gauge theory up to subpolynomial or a fractional time scale, which we call tau adjusted, is proportional to the square root of V over V naught cubed. So V naught is some energy factor that depends on the microscopic parameters of your model. And V is the energy protection strength. So you see there's absolutely no size dependence here. And your adjusted gauge theory looks as follows. It's an exact gauge theory. So you can prove this using constrained dynamics. A renormalized gauge theory up to exponential timescale can be shown to exist also in the thermodynamic limit with the following timescale. This we cannot access numerically, unfortunately, but the adjusted gauge theory we can. But already the key message here is that analytically we show that you have at least up to tau adjusted, this time scale, you have an exact gauge theory that will approximate your dynamics well, your dynamics under the Foldy theory well. Can we see this actually in actual results? And the answer is yes, as we will see in the following. Let's take a concrete example. I will take the spin S U1 quantum link model. So what I mean by spin S is that the link which simulates the gauge field and the electric field now is a spin S matrix. That's the whole point of quantum link models. So here we see that these S operators are spin S operators and the sigmas are Pauli matrices that describe the matter field. Again, this is the assisted pair creation term. So I create an electron-positron pair and the electric field has to react in the middle to preserve Gauss's law. SC here is the electric field. If you're using spin 1/2, this is an inconsequential constant energy term. Anything above spin 1/2, then this actually will factor into the dynamics. Gauss's law takes the following form. So here it basically tells you, depending on the matter occupation that you have here, which is given by sigma zj plus 1 divided by 2, depending on this matter occupation, your electric fields on the adjoining links have to point in a given configuration to keep Gj equals 0, i.e. to stay in the sector of Gauss's law. And experimentally relevant gauge breaking terms are the following. So unassisted creation of electron-positron pairs or unassisted flipping of the electric fields. These are local gauge violating terms. Now, the full protection term, as I have mentioned, and as I have shown you results for so far, is the following one. You just take the square of the generator of Gauss's law, and you add it to your quench Hamiltonian, and this penalizes any processes going outside of the sector of Gauss's law. But we also found out that you can do something extremely simple and in a way stupid. You introduce the following linear protection term, which is as experimentally easy to implement in your ultra cold atom setup as H0 itself. So you just take a staggered configuration of the generator of Gauss's law. You sum over this alternating configuration, and this is your protection term. So in terms of experimental feasibility, this works extremely well. It's very simple. The only problem is now your adjusted time theory, at least according to the worst case scenario, will persist up to a system size dependent timescale. This is a bit of a problem, but as we will see now in the results that I will show you, exactly for this term, we get qualitatively, for the short timescales that we can access in infinite matrix product states, you get the exact same behavior as this term qualitatively. And without any further ado, here are the results. So here what I'm showing you, the only difference between any two panels is the size of the link spin length. So we go from spin 1/2 to spin 2. And the red curve is without any protection. So I'm setting my violation to lambda equals 0.1. And you see that this just keeps growing as lambda squared t squared until it starts saturating to a maximal violation value. And then here I show you the different values of V. And again, this is all in the thermodynamic limit because infinite matrix product states work directly in the thermodynamic limit. You see a suppression in the plateau of your gauge violation as lambda squared over V squared. And this time scale happens at 1 over V. It's proportional to 1 over V. Yes, we do not have times up to 10 to the 5 like we do in exact diagonalization. So you may tell me, okay, you're doing great for these accessible times. What happens at later times? We will answer that in the next slide. However, let me point out that already this time scale here for typical experiments, this is roughly 120, 150 milliseconds, which is at least what we are doing right now in Heidelberg in our experiments, is like the largest times you can go before decoherence kind of kills you and you can't see what's happening anymore. So already these are good results for modern analog quantum simulators that are putting out the latest experiments on these gauge theories. However, let's see how this gauge violation behaves with system size. Here I show you.
Before you continue, can I ask?
Yes.
So what you showed on the previous slide is all for the linear.
Yes.
Right?
Yeah.
So can you explain again what the advantages of this over the, because okay, you said the disadvantage is that the time scale is, goes with L. But what is the advantage? Is it easier to implement?
Yes, it's absolutely easier to implement. Okay. So if you look here, GJ, this is a single body term.
Ah, right. Okay. Yeah.
When you have GJ squared, then experimentally this becomes harder. So what I would like is I would like something to implement that is at least as hard as H0, as the ideal theory, right? The experimentalist already has a hard time constructing an extended system like this. So far, most papers have done these tiny building blocks. So just a unit cell of one matter site and a link or two links where they can implement a local constraint. I mean, this is the difficulty in these problems. It's not like you just have a simple Bose-Hubbard model where you have your particle number conserved. So you have this global U1 symmetry. And basically, so long as you're not losing atoms, it's conserved. No. So here, the gauge symmetry is local. So at each local constraint, so a matter site with the adjoining links, you have to make sure that such a conservation law exists on that tiny spatial scale. This is what makes things really harder. And that's why errors like lambda H1 are unavoidable. So the easier we can make it for the experimentalist, the better. And that's why this term is significantly more advantageous or more attractive here than the full protection term. But really, if you look at this paper, which came out last week, and if you look at this result for the linear protection or the full protection, you have to kind of go back and forth to see that they're not copy-paste of each other. So qualitatively, they're really the same. So I think here I'm including the results for the linear protection, but actually, if you now replace it with the full protection, I wouldn't be able to tell the difference. And now, again, we go back to the finite size behavior, and we see here something really cool. So again, this is for the linear protection, which basically should, in the worst case, should mess up in the thermodynamic limit, and we see it doesn't. So the L goes to infinity limit, the thermodynamic limit result, calculated in IMPS, is juxtaposed with the following exact diagonalization calculations for 2, 4, and 8 matter sites, respectively, for spin 1/2. And for spin 1 with 2, 4, and 6 matter sites. And what you can see is for all the accessible times that we have, already at 4 matter sites, you're falling exactly on top of the thermodynamic limit result. This is quite spectacular, yeah? This is quite spectacular because this linear protection term, at least analytically, in the worst case scenario, is not supposed to work there. But actually, we see that when your errors are local, you have a good shot, and they do work. And not only do they just work well, they already give you what you would get in the thermodynamic limit. Now you may tell me, okay, you've only been looking at the gauge violation. Why don't you show me something else? And I will be like, okay, we can do that. And here I'm looking at the matter density, right? So I'm telling you about, I have this matter creation in the form of electron-positron pairs, which starts at 0. And now I'm just tracking how it evolves. So the ideal theory, which in this case is also the adjusted gauge theory, because the H1 that we have used here completely takes you out of the gauge invariant sector. So the term in the adjusted gauge theory, let me go back to this because maybe I did not explain it completely well. So here P naught is a projector onto the Gauss's law sector. And if H1 takes you completely out of the sector, then this term would go to 0. And so here you see we have the dynamics under the ideal gauge theory in thick red line. And then also with the faulty theory, i.e. I have a finite lambda and a finite V. And we see that already at V equals 10, we have, so the line lies on top of the ideal theory dynamics. And if we look at the deviation of the dynamics under a protected faulty theory with respect to compared to the ideal theory, you see that we grow as t squared, and then as time proceeds, we go as t. So in the worst case, our error bound from the analytics tells you that you would grow as t squared, but actually you see that as time proceeds, this we beat that bound, we do much better. So the error growth is much more benign than the worst case scenario predicted by our analytics. And as you can see here, you have a suppression of 1 over v in your deviation. So this is also great news because again, I see that I can reliably simulate my dynamics beyond just the gauge violation. So this N is much easier to measure in the lab actually than your gauge violation. And what happens here is that, okay, at a relatively small V, I can already reproduce up to long times my ideal dynamics in a faulty gauge theory. If we look at the finite size behavior of this, again, we see that at just a few matter sites, I can come very close to the thermodynamic limit result. This is, again, I must emphasize that this is quite exciting because when you do a gauge theory, you really want to try to go to the continuum limit and the so-called Kogut-Susskind limit. So the Kogut-Susskind limit means that I want my quantum link to have as large a spin as possible. This is the QED limit per se. They also call it the QED limit. Or rather the lattice QED limit, because the QED limit would also entail taking the continuum limit. But however, as you see, between S equals 1/2 and S equals 1 in the gauge violation, we also have no problem. So if we go to the gauge violations here, you see that going from S equals 1/2 to S equals 2, the gauge violation at a given value of V is not changing so much. In the worst case scenario, the protection strength is predicted to go as S squared. But in our numerics, and we've tried many different initial states and many different local errors, we see that S actually has no adverse effect on what size your protection strength should be. All right, so now comes the last part of the talk. And the question is, what if we completely turn off this protection? I just want to say, okay, look, I don't want to bother myself with building this protection term. I just want to live with whatever fine-tuning imperfections I couldn't solve. And can I get something? Can I still get some gauge theory dynamics at least up to a given timescale? Let us take a simpler gauge theory. So the gauge theory that I showed you earlier, the local generator has 4 different possible values or eigenvalues that it can take. Let's take something similar. So let's focus on the Z2 gauge theory. Here, again, we have this assisted tunneling term or assisted creation term, but now in terms of hardcore bosons. So the matter fields are modeled by hardcore bosons, and the gauge field is a Pauli matrix, tau Z. Your electric field is tau X. These are just details, but basically Gauss's law takes on the following form. So GJ can only have 2 values, 0 or 2. And of course, H0 is gauge invariant according to this relation. And this is inspired by an experiment done in Monika Eidelsburger group, Schweitzer et al. In Nature Physics, if you want to look up the paper. And they do some Floquet implementation where they shake the lattice at a given driving amplitude, and they can come up with a building block of the Z2 lattice gauge theory, with the following errors that they classify really well in their paper. Now, what we will do is we will just assume that we are able to build an extended model of their system with the following errors. So these errors are local gauge violating errors that basically will drive your dynamics out of the GJ equals 0 sector. So what I'm going to do now is I'm going to choose an initial state in the Gauss's law sector, and I'm going to quench it only with H0 plus lambda H1. I'm not doing any protection. So now we forget about protection. Before we continue, I would like to introduce a small glossary. I will be mentioning quite a bit a gauge invariant supersector PM. Okay, so PM is the projector onto this gauge invariant supersector. But what we mean by this, it's the set of all gauge invariant sectors with M violated local constraints. Pictorially, what we mean by this, so imagine every matter site, every white matter site indicates that Gauss's law is preserved there. If it's red, that means it's violated. So in the gauge invariant supersector M equals 3, basically I have exactly 3 of these local constraints broken. All right, and these are possible configurations of them. The result is the following. So I start in an initial state where Gauss's law is satisfied everywhere. The blue matter sites indicate that I have one boson there. The white means that they are empty. And I have the field in the following configuration, okay, in order to satisfy Gauss's law. So I end up with a staggered electric field and a staggered occupation of the bosons. Again, I emphasize that the initial state does not affect the results that I'm introducing now. We tried it for many different initial states. You can look at this longer paper. We try it for many different initial and boundary conditions, and we get the same conclusions. And the intriguing and fascinating conclusion is what follows. Again, as before, we see that the gauge violation grows as lambda squared t squared at early times. But amazingly enough, we see that we enter a cascade, or what I call a staircase of plateaus, pre-thermalization plateaus, we call them, at time scales of 1 over lambda to the s, where s is an integer that goes from 0 to L over 2. And L, as we have shown before, is the number of matter sites. So here, this is exact diagonalization results for L equals 6 matter sites. And you see I have 3 plateaus. And the smaller the value of lambda here that you see, the longer lived these plateaus are. In the insets, what I show you is I'm just rescaling, I'm just doing a time scale analysis. So T lambda, a time scale of 1 over lambda, you see that all these plateaus at different values of lambda coincide here. You see for the smaller lambda is the longer lived this plateau is, as we mentioned. Again, for T lambda squared, the next set of stairs coincide. And when I rescale by lambda cubed, my time axis, the last set of time scales coincide. All right, let's try to see this pre-thermal behavior in other observables. If we look at the projectors onto the gauge invariant supersectors, so here P0 tells you basically this is Gauss's law sector, the sector of Gauss's law, I have no violations. P2 means I have 2 violations, P4, 4, P6, 6. You see there's no odd, there's no P3 or P5, and this is because H1 does only even breaking. So if you break one constraint, you have to break the neighboring one, according to the form of H1 from that experiment. But interestingly here in P0 and P6, you see that they have 3 plateaus as well. So here, if we zoom in on P0, you see that at a time scale 1 over lambda, we go into the first plateau. At a time scale 1 over lambda squared, we go into the second. And at a time scale 1 over lambda cubed, we go into the final and third plateau, same as P6. While P2 and P4, they have only 2 plateaus. This is just because of the availability of processes taking you out of this sector, the sector that you are in. So when you are at 0, you have 3 different sectors that you can actually go to. When you are at P2 or P4, you have 1 less, and that's why you only have these 2 plateaus here. Also, you see, you can convince yourself in time-dependent perturbation theory that depending on what sector you are projecting onto, the projector grows in value as lambda t to an even power, where this even power is the number of gauge violations that you have. or the number of constraints where Gauss's law is violated. So P6 grows as lambda to the 6t to the 6, P4 grows as lambda to the 4t to the 4. So the detailed calculation for this in time-dependent perturbation theory is found in the second paper here. How about if we look at some local observable? Okay, let's look at the staggered magnetization, at the staggered boson number. So if we go back to the Hamiltonian real quick, this guy actually preserves a U1 global symmetry. So it has a local Z2 symmetry, the gauge symmetry, but it has a global U1 symmetry in the form of conserved boson number. And so if you look at the boson number, you're not going to see any dynamics because H1 also does not break it. But if you look at the staggered boson number, again, you see this interesting plateauing behavior at these different timescales. Okay, and again, we do the timescale analysis here, T lambda squared, T lambda cubed, and you see them falling on top of each other. Now, can we get some kind of analytic explanation for this? So time-dependent perturbation theory does not. As you have seen so far, if I just want to focus on the gauge violation, which is a gauge invariant observable, time-dependent perturbation theory always gives me terms proportional to lambda t, all to the power, all to some even power. Okay, so your timescale from time-dependent perturbation theory for gauge invariant observables is always 1 over lambda. That's the only timescale that you will get from this. So I need something more. So what I'm seeing now is non-perturbative. These pre-thermalization plateaus are non-perturbative, and I would like a non-perturbative treatment for them. As such, we go to a Magnus expansion. What I do here is I write my full time evolution operator in the following form. So this exact rewrite up of my time evolution operator splits the gauge invariant dynamics in H0 and restricts any dynamics that will take me out of the sector of Gauss's law in this term, in U tilde. And now what I want to do is I want a Magnus expansion in U tilde of t in terms of this Q Hermitian operator, omega of t. And now the Magnus expansion entails just doing this infinite summation, or we're not going to go to infinity, of course, but basically each order of the Magnus expansion is itself an infinite resummation of terms from time-dependent perturbation theory. This is why the Magnus expansion is much more powerful, and it will give you dynamics that are just simply inaccessible in time-dependent perturbation theory. So omega 1 and omega 2, we're only going to consider these two because otherwise the analytics gets really ugly. And anyway, already at third order, there's a lot of numerical overhead to simulate the dynamics with the Magnus expansion. We're not going to go there. So an important thing to note is usually Magnus expansion, to see if it really converges, you have to actually check this analytically. And that's what we're going to do right now. We're going to check our time evolution from the Magnus expansion with that we did in exact diagonalization. And we will see how they match really well. So let's look first at omega 1 and omega 2. And you see that analytically, you get the following terms. So don't let them scare you, because I will just explain this. This is just a formality. I will just explain the main point here. So by alpha q, I mean a common eigenbasis of H0 and Gj. As you know, H0 is gauge invariant, so it commutes with Gj. I can find a common eigenbasis for both, and I will call it alpha q. Alpha is basically indicates the gauge invariant sector you are in. So basically, you can think of alpha as a vector whose components are equal to, so it has as many components as you have constraints or matter sites. And these components can take on the value of 0 when Gauss's law is satisfied, or 2 when Gauss's law is broken at that constraint. And Q stands for all other good remaining numbers, good remaining quantum numbers. So you see that we can split now the first order Magnus term into two components. And here, this is crucial. One component is a non-resonant one. And you see we have this oscillating term here. And another component is a resonant one, which takes the following form. Okay, good. We see now, at least in the system sizes that we have reached, and we did here 4 matter sites and 6 matter sites for the initial state that I showed you originally. We find that these energy differences here are either exactly 0 or above 0.01 J. Okay, there are a few between 0 and 0.01 J, but my point is either they are exactly 0, and then they go into this term, the resonant term, or the difference is so big that this term washes out very quickly in the time dynamics. Okay, it washed already at T greater than 1 over J, they're gone. What this term does is it generates your dynamics. So you can calculate this term because its norm is bounded. You can actually get it in TDPT. So time-dependent perturbation theory would reproduce the dynamics due to this term. And if we look pictorially here, we see that this term is responsible for the growth 1 here. So what I'm showing you here in this figure, which is very important, I'm showing you 2 values of lambda, 2 values of the gauge breaking strength, 10 to the minus 3 and 10 to the minus 4. 10 to the minus 3 is just for reference, for you to see the difference between the peaks here. So this is for 4 matter sites, actually, in this case. Here you see 2 orders of magnitude between these 2 peaks. So 1 over lambda squared, the time scale. Here it's just 1 over lambda. There's 1 order of magnitude difference between these 2 peaks. And these 2 results, so in orange and dotted green, are exact diagonalization, and the other curves are different orders included in the Magnus expansion. So you see, when I include only omega 1 non-resonant, the light blue one, light thick blue one, you see that originally, before this term averages out to 0, I have some growth in my error until I hit a plateau, the following plateau here. Nice. Now comes omega 1 resonant. So omega 1 resonant of T, notice very importantly that it has also a time scale of 1 over lambda. This term, you cannot get it in time-dependent perturbation theory because its norm grows as T lambda. However, if we use this to simulate the dynamics, it's actually a time-independent Hamiltonian, because according to the Magnus expansion, the effective Hamiltonian due to this resonant term is simply I omega 1 resonant divided by T. So you just get lambda, blah, blah, blah. And this time-independent effective Hamiltonian will take you out of this, what we call pre-onset plateau, so here, and it will drive the dynamics 3 up to a time scale 1 over lambda, where then this term basically takes us into a plateau. Good. Now we go to the next term, omega 2 resonant. I'm not going to show you the non-resonant one because it's not important. You see omega 2 resonant, the crucial thing here to observe is that you have the term T lambda squared here. So this gives us the time scale of 1 over lambda squared. And once I reach this time scale, what happens is that omega 2 res is the culprit behind taking me out of this plateau 4, which is the onset plateau. It takes me out of it until a time scale of 1 over lambda cubed when I hit this this plateau 5. Now, if I make my system bigger, omega 3 resonant, which would be proportional to T lambda cubed, I'm not showing it here, but you can see it in this paper and you can easily convince yourself if you do this derivation, you would get T lambda cubed. For omega 4, you would get T lambda to the 4, so on and so forth. And this exactly explains the plateauing behavior that you are seeing, the staircase pre-thermalization. But now you may tell me, okay, look, I mean, the formalism that you just did right here, you can apply it exactly for a model with global symmetry. You don't need a gauge symmetry. You can have a global symmetry. You will get the exact same formalism. I tell you, yes, you're right. But the interesting thing here, if we look at the table, if you look at a gauge symmetry with the perturbative breaking that we talked about with L equals 6 matter sites, and a global symmetry model, here we use the Bose-Hubbard model with L equals 12 sites. So these are equivalent because remember, I'm using periodic boundary conditions. So 6 matter sites means I have a total of 12 spin sites, if you wish. And what we see is that the resonances between the different supersectors. So here, when I say E02, that's a resonance or a transition between the supersector where I have no violations and the supersector where I have 2. 020 is a second order process in H1, which basically takes me from the 0 supersector to the one with 2 violations back to 0, so on and so forth. What you see is that the non-zero minima here in E02, so remember we have 2 crucial ingredients. Either we have an exact resonance, so the number of states with E equals 0, or we want these energies to be larger than a certain threshold so that the oscillating term washes away quickly, so that it doesn't destroy these pre-thermal plateaus. The bad things for these pre-thermal plateaus are these non-zero minima between 0 and lambda threshold. So lambda threshold, we set it as 0.01 for this table, 0.01J. You see that the non-zero minimum here is roughly 2 orders of magnitude bigger than the corresponding transition non-zero minimum in the global symmetry breaking case. Now you can tell me, okay, but as you go to larger and larger system sizes, these non-zero minima will become smaller and smaller, and indeed they do. But the good news is, when it comes to local symmetry models, or lattice gauge theories in this case, you have a lot more degeneracies due to these local constraints than global symmetry models. So that means as you go to larger and larger sizes, your degeneracies will increase more and more. And this may be a balancing act to the decrease in these non-zero minima. But the bottom line is we are not sure if the staircase pre-thermalization, we cannot make a definitive statement about whether or not this staircase pre-thermalization will persist in the thermodynamic limit. But already this is quite interesting for the current system sizes accessible in modern experiments. But if it does really persist in the thermodynamic limit, this is quite interesting in that one can ask, what do these plateaus actually mean? So if we go back here to the original figure, what does this, so here I have plateaus where the gauge violation is absolutely not growing, it's just stuck. Can I actually model this as a renormalized gauge theory? Can I find a renormalized gauge theory here, even without any kind of protection? So what we introduced, the earlier results show that we only have a renormalized theory when you have a protection term. Otherwise, your gauge theory is gone. But here I see that my gauge violation is basically stuck. It's not getting worse. And it would be interesting to try and model this with a renormalized gauge theory. This is something that we are thinking about right now. We're also thinking about a hydrodynamics treatment to see what's happening here in between plateaus. And we want to extend our results to more general gauge symmetry models. So basically, this brings me to the summary of my talk. Basically, what we have looked at today is the enforcement of gauge invariance in models in the thermodynamic limit, where basically we have unavoidable experimentally relevant errors. And we showed that gauge invariance can be very cheaply implemented, even in the thermodynamic limit. And we also looked at this cool staircase pre-thermalization effect. And we see that it may indicate some really interesting physics at these plateaus that we are working on and trying to understand even better. So I hope I didn't extend my time, but if you have any questions, I would be happy to take them now. But before that, I would like to mention my following collaborators. So my boss, Philip Hauke, Haifon Lan is a PhD student that I am co-supervising with Philip. Julius Mildenberger is also a PhD student in Philip's group. And Martin van Dam is our numerical whiz in the Frank Verstraete group. So we have a lot of fun with him on many numerical stuff. And thank you very much.
All right, thanks, Jad. So, well, some people, including myself, have to go pretty soon. But if anybody has any questions, see you, Juan. So, if anybody has any questions, ask now.
I think Juan wanted to ask a question.
Well, I think he wanted to say goodbye because
okay,
goodbye. But let me ask a question, actually. Because I really do have to go pretty soon.
Okay.
So, you had this plot of the expectation of P0, P2, P4, P6, and so on.
Mm-hmm.
And you sort of scroll back to show it. So I may have, I definitely lost you. I couldn't follow the details. But okay, so you said that from 0, you have 3 sectors you can go to, right?
Yeah. So,
okay. I understand the high level, but I don't understand why you said.
Sorry.
So what are you calculating here, actually?
What
system? Sorry, what system?
So forget about how many local constraints you can go to and stuff like that. Let's simplify it. So P0 is really, so you have your time evolved state, and I'm just taking the expectation value of a supersector projector with respect to this time evolved state at different points in time, right?
Mm.
So P0 tells you how much of your wave function is still in Gauss's law. So ideally, you want this to be one forever, actually, in an ideal gauge.
I get that. I guess what I'm asking is, what is the system sorry, what is the system, the actual, so what system size are you looking at? Why do you see
6?
But okay,
that's why I can have. Go ahead.
No, yeah.
So
I think you are going to answer my question.
P6. Okay, so I can have 6 violations at most because I have, the number of matter sites is the number of local constraints that you have.
Yeah.
So since I have 6 matter sites, I can only have 6 violations at most. And of course, at least I can have 0. P2.
So you said that from 0, you have 3 ways of, right?
Well, I mean, okay, it depends on what order process that you have, right? So a first order process would take you to 2, third order takes you to 4.
You're in
so on and so forth.
Orders, not leading order in your. Oh, I see. That's what I didn't get. I see.
Okay.
I see. Whereas from the others, you have to. Okay, I see. Yeah. Okay.
I mean, from 2 to 4, it's 1 order, and to 6, it's 2 orders, right? So that's why you see these 2 plateaus, same as for 4.
Yeah, I get it now.
You can't do anything else.
Yeah. Okay. Thanks. So sorry. I mean, I actually have more questions, but I really do have to go.